All right, as you can see, we are covering now section 2.3, chapter 2, section 3 of our book. So I'm going to jump right in like always and spend the first kind of half of this hour or so going over some PowerPoint slides just to give you kind of an overview rundown of this entire section. And then I'll jump over to the homework assignment in my math lab and we can look at the rest and do some, a handful of problems like always. So we're talking about continuity today. And we've been dealing with limits and functions and dealing with all that. Now we're going to talk about what it means if something is continuous. And I might have mentioned this before, but we'll go over it again. They give you a nice definition here at the top where if you can draw the figure without removing a pen from paper or pencil, if you can just draw your figure in one continuous motion, it's considered continuous. That's the continuity that we're talking about. So if it's continuous at every single x, and you'll see there'll be exceptions where sometimes there is no, there's continuity everywhere, but it's not continuous at one point, that's a different story. But if it's continuous everywhere, then one thing we've talked about this before as well, your limit down here of any number, approaching any number, if you have a continuous function, if you determine it's continuous, then the limit is basically the y value, whatever you plug into the function. So if you're looking for the limit as x approaches 2, literally just go find f of 2 and you have the limit. Okay, now we take a case where this is a non-continuous, not a continuous graph, and you can see there's a hole right there at x equals 2. So it says here, you're reading if it's disconnected at a point C, it means it's discontinuous. There's a gap. There's a hole right here at x equals c, whatever, any value, any particular value. So everywhere on our function it's continuous except that one point. So if we're talking about -3 right down here, the function is continuous at -3. So even though the function may not be continuous, if I'm asking you what's the limit as x approaches 3, as long as it's continuous right there, or -3, I'm sorry, as long as it's continuous right there at that one point, so both sides have a nice smooth, continuous graph, then the limit, is the same as the f of that number. Okay, it is just plugging it in and getting your answer, like in this last graph right here, where if you're looking for it at 2 and it's continuous at 2, you can plug in f of 2 and get the y value of 4. But now in this graph, you'll see it's not continuous right here at x equals 2. And the reason is, look at the original function. If you plug in 2 to this, you get a 0 on the bottom. That's why there's a hole there. Whether it's a hole or it's an asymptote or, a big gap, a big jump, it doesn't really matter. It's not continuous right here. Okay, so your first choice usually is, well, let's plug in 2 into the function, see what we get. And that's kind of an indicator right there. If it's not defined, then we have to do some more work here. So what do? So remember, if it's continuous anywhere else, it's continuous any other interval that does not have 2, then you're fine, except for that 2 is your problem. So how do we do it here? Okay, well, I didn't go through this here, but let me just go and give you an answer here. The starting answer is go make a table and just see what happens as you get really close to 2 from both sides. Remember our two-sided limits here? So if I make a table, and we know that 2 doesn't exist. So I'll put a big line right there. So what I want to know is, what's happening at 1.9? What's happening at 1.99? 1.999. This is coming in from the left side. Okay, as we're approaching this way right here. 1.9, 1.99 right here, really close. We're seeing what y values happen, and we're trying to see, is there a pattern here? And then on the other hand, do the same thing. Let's plug in numbers getting really close to the number 2 from the right side. And you can pick anything you want. This is coming in from the right. And again, what is the pattern? Hopefully they're both going there. And if you try this out, you'll find both values are going to get closer and closer to the y value of 4. That's how you know that's your limits. Okay? Now we go to another picture that we've kind of dealt with in the beginning here. And I know we jump back and forth in these, so you'll get kind of a reminder of this. This is one of our graphs where it's got two different halves, two different sections. These are our piecewise graphs. We're going to do a little bit more of those today as well. So on this piecewise graph, when you're looking at it, it's the same thing. Okay, we want to know what's the limit as x approaches 0. And clearly you can see it's discontinuous at 0 because you have to lift your pen or pencil when you're drawing this graph. It's good on the left of 0, it's good on the right of 0, but right at 0 there's a big gap. We don't know what's going on, so we need to find out what's going on there at that exact point. So you see at the bottom, the limit does not exist. H of 0 is not defined. Now the reason the limit doesn't exist is as you come in from the right side, it's approaching the number 1, the y value of 1. As you come in from the left side, you're approaching -1. So remind you of the notation. As you approach 0 from the right, it's getting closer and closer to the number 1. It's always 1, in fact. But as you approach x from the left side, approach 0 from the left, same function, but this time you see down here, it's approaching -1. So those two limits exist. The limit from the right is 1, the limit from the left is -1, but in order to have a limit as x just approaches a plane 0, these two have to be in agreement. Okay, so from the right and the left, they're both approaching the same number, then that's our answer. But here, this one does not exist because you're getting two different values here. So I wanted to make sure we're clear why it doesn't exist. It just says it here at the bottom, but this is the reasoning. Okay? Okay, so continuous everywhere except, the function h is discontinuous at 0. It's continuous over every other interval. So any other point you're trying to find the limit of, because there's continuity at 1, at 2, at 3, or at a half, or at negatives, every other x value, there's continuity. The graph is continuous, so you can just go plug it into the function, this one right here in blue, and you can get your limit. But when you're at a place that it's discontinuous, then you have to do some extra work. Like I just did the finding out limit from both sides or whatever, making a table. You have to do more work when the function's not defined or when it's not continuous right there. Okay, so function is continuous at the point if x equals c. If, a couple things here, if the limit exists, then you know it's going to be continuous. Okay, and you have to get this point right here that exists, and it's going to be the same. So if these three things happen, then you know you have continuity at that point. Now, you can just eyeball a graph. You can see if something's continuous, or you can graph it, or you're going to learn from looking at the functions. But these things go hand in hand. If you know something's continuous, there's going to be a limit. It's going to be f of whatever that point is. They're going to be the same. Okay? All right. So if one or more of the three conditions in the definition fails, then it's discontinuous. Okay? There's no continuity there. So if any of these three don't work, then you won't have it. So now you look at the next picture here. You can kind of look at these things. And you got to make sure you're clear of what's being asked. So let's look at this -4. Okay, first, do we all see there's a discontinuity right there because there's a jump? So there's definitely a problem right there. Okay, so if you take the limit as x approaches 4 from the left side, just kind of follow this graph as you get closer and closer to -4. Look at what y value you're hitting. Looks like we're hitting a y value of 2. That's why the limit from the left, that little negative, approaching -4 from the left, it's 2. Now the limit approaching 4 from the right, go in this arrow, just follow down this picture, and it's approaching this dot, which is 3. There's a limit from the right. So therefore, like the last example, the limit as x approaches -4 does not exist because these 2 points are not in agreement with each other. Okay, then we look at what's f of -4, and this is where people get tripped up a little bit, where they know how to do this, but they're so used to these limits. This is just simply asking, what is f of -4? Go to the function, plug in -4. What's the y value at -4? So we go to -4. We don't have a function, but we look at where's the dot. That's an open dot. The actual point on the function is right here. It's at 3. Okay? So condition 1 in the definition of continuity fails. So therefore, you have no continuity right there. So go back to these things right here. In order to be continuous, the limit has to exist. We just showed right here the limit does not exist, that proves that there's a discontinuity right here. Now, like I said, you can look at the graph and you know there's a discontinuity. So if you look at a discontinuity, go back to our 3 points, one of these or more is going to fail. Okay, f of c exists. Well, we just found that there is an f of -4. It was that 3. That exists. So this is okay. All right. The limit, obviously, the limit didn't exist. So that's our fail right there. And also, of course, the limit doesn't equal. If it doesn't exist, it can't equal. So these 3 criteria, if you want to call it, they go hand in hand with something being continuous, talking about the continuity. Okay, so condition 1 fails. All right, so let's look at -2. Now there's a discontinuity right here just by eyeballing it because we can see there's a gap. There's a little hole right there. So let's look at what we get. When we find the limit from the left, it's approaching y value of 5. When we get the limit from the right, it's also approaching 5. So the limit actually exists because from both sides you're approaching 5. Remember, the point doesn't have to exist, just for a limit. A limit will exist as long as from the left and from the right they are approaching the same y value. They're both approaching 5. So criteria 1, the limit does exist. All right. The point at f of -2 does not exist because there is no coordinate right here at -2. So therefore, condition 2 fails because there is no point. It doesn't exist. So if there's ever a place where the point doesn't exist, that's an automatic discontinuity. Now our last one we're going to look at here, we're going to look at a couple more. Let's look at 1. Approaching from the left, the limit is approaching 5, 4. Sorry, they got that wrong right there. 1, 2, 3, 4. This y value that it's approaching is 4. We'll fix that. That's supposed to be 4 right there. On the slide, my apologies. Yeah, they're not going to let me fix it, sorry. So I'm just going to go by that. It's 4. All right, the y value as we come in from the left side, it's approaching the y value of 4. I'll just put a little 4 right there. So make sure if you do happen to view this slideshow later on, you know that there's a mistake right there. That's supposed to be a 4. Okay, and okay. So second thing, let's find the limit coming from the right. So remember, follow your function. As you're approaching 1 from the right side, it looks like it's approaching a y value of 1 also. So the limit from the left is 4, the limit from the right is 1. If they do not equal each other, then the limit doesn't exist. And f of 1 also doesn't exist. So you see here, conditions 1 and 2 fail. And by definition, if you don't have a limit, then condition 3 is going to fail as well. Okay, so let's see if they can get this last one correct. Discontinuity at -3 or +3. Now again, you see it. There is a point right here at 3, but there's a little hop. You're drawing, you got to hop down to here, then hop back up. So there's a gap. That's why there is a discontinuity right there from the picture. Now let's look at our limits. From the left side, we're going up this graph. Remember, you're tracing along the graph right here. Okay, so you're tracing right up here. And what is the y value approaching? Well, from the left, it looks like it's approaching a y value of 3. From the right side, coming down here, it looks like it's also approaching the y value of 3. Therefore, the limit exists, and it is 3. But f of 3, remember, f of 3 is not asking a limit. It's asking what's the actual coordinate at x equals 3. The coordinates way down here, it's a y value of 1. So therefore, the first condition works because the limit exists, it's 3. The second condition works because the point exists, 3, 1, but condition 3 fails because those two values are not equal. Okay, and that's why we do not have continuity there. Okay, so use the definition of continuity to discuss the continuity of the function at the given point. Well, the function is f of x equals x plus 3 at x equals 4. The solution is it's continuous because the limit as x approaches 4 is 7. It's getting closer and closer to 7 from both directions. If you make a table and get 4.1, 4.01, or 3.9, 3.09, sorry, 3.99, you're getting closer and closer to a y value of 7. And then, of course, if you just plug in 4 to the function, you get a 7. Since they're equal, it's continuous. Now we're going to talk about this one for continuity. Now, I'll give you a little shortcut without going through all the definitions. Start with, does it exist? Start with number 2. If you're just checking continuity, plug in the function, -3, the x value, to the function. If it makes a bottom 0, then right there, you know the point doesn't exist and there's nothing more to check. There is no continuity. You can't have continuity if there's a gap. It doesn't matter if it's a hole or it's an asymptote or a jump. That's discontinuous. Okay, now we have this one. Same kind of thing. When I plug in 1 in the bottom, I get a 0 over 0. I don't really care so much about the 0. I just care about the 0 on the bottom. That means the point doesn't exist. So the fact that the function is not defined at 1, that's enough to say a discontinuity. If you want to go a step further and find the limit, we did a function like this earlier. From the left, it's going to approach, I think it's 1. Yeah, from the right, I'm sorry, it's approaching 1. From the left, it's approaching -1. Because the two side limits don't meet, they're not the same, then the limit doesn't exist. Okay, so a couple other things. They say a function is said to be continuous on the right if you're taking the limit from the right and it's approaching the actual value. So I'm going to go back to that graph that we had earlier. So let's take this -4 right here, okay? Ignore what it says here on the left. Just look at the picture. If I'm looking at -4, if I come in from the left, the limit, the y value that I'm approaching, is 2. However, f of -4 is not a 2. That's why there's no continuity from the left side. However, from the right side, if I check my limit coming from the right, it's approaching the y value of 3, and f of -4 is 3. So because the point equals the limit, then it's said to be continuous coming in from the right, not from the left, and definitely not continuous in general. So these ideas of continuity from the right or left side, I'll tell you, they're not the most important thing. They're good to know, but it's not going to make or break you, because the most important thing is, can you just tell if something's continuous or not? Okay? A function is continuous on a closed interval if it's continuous both right and left side. That kind of makes sense. We kind of already knew that. The limits don't meet at the same number, then it's not going to have a limit and it's not going to be continuous. So it's kind of a repetition there, but it doesn't hurt to have different angles to look at these. Okay, so a couple other ones here. I'm going to jump through a few just to get to some. You won't need all of these because some of these are going to be kind of obvious to you, and we're going to see them when we do some of the problems in a second here. A couple of these, like this b for n is a positive integer. If you have this, it's going to be continuous all the time, as long as this is a positive integer. Just so we're clear, x to the first, the second, the third, the fourth, the fifth, the sixth, all the way up forever. A positive integer means no fractions, no decimals, and no negatives and no zeros. So as long as you get a function that just has a bunch of, remember the polynomials we mentioned a couple days back, as long as it's just a polynomial with nice positive powers, you have continuity all the way. Okay? That's the C they're talking about there. Rational function is going to be continuous everywhere except for the places that make the bottom 0. Then you start getting these roots here, and they're pretty much going to be continuous wherever the function is continuous. Okay, so what that's saying is wherever the inside is continuous, the entire root's going to be as well. So if you have a square root, a cube root, any of that. And then if it's an even number, of course, it doesn't work when the function is negative. So that's why they're just saying it's continuous when it's non-negative. Okay, so let's get to some actual examples here. Here we have a polynomial. I see 3 terms. That's a power of 2, that's a power of 1, that's a constant. Therefore, every piece is going to be continuous, so the whole function is going to be continuous, and it's going to exist everywhere. The answer is this thing is going to be continuous for all x, or from negative infinity to infinity if they ask for an interval notation. Here we have a rational function, and remember, it's continuous everywhere except where the bottom is a 0. So if you set the bottom equal to 0 and it's already factored, it's not going to exist at 3, not going to exist at -1. So we say it's a rational function continuous for all x's except for 3 and -1. And just to kind of show what we're talking about here, if they ask you to do this in interval notation, which sometimes they'll do in my math lab, that's supposed to be at infinity. It means we go all the way up to -1 and not including -1. And we have a union. We pick right back up at -1 and we go all the way up to 3, again a parenthesis. And then we go from 3 to infinity. So you see, it just means we're skipping this, we're skipping that. It basically means all real numbers except for those. And I bring that up, like I said, because there are going to be problems where they're going to ask you to answer continuity or domain you've probably already seen in interval notation. So it doesn't hurt to have that in the bank there. Okay, so remember now, when you have a cube root, there is no restriction on what can be in the inside. Every point exists, positives, negatives, fractions, decimals. So because this entire function inside is continuous already, x squared minus 9, a cube root means it's going to be continuous everywhere as well. Now the next one, you see we have a square root. So even though x plus 1, the inside is continuous everywhere, we can't have it anywhere else except for positive parts. So the way I do this is I take the inside and I say it has to be greater than or equal to 0. We can get it 0, we can get it positives, we can't get negatives, so I just solve this and this is my answer. It's going to be continuous because this is the only place the domain exists, but it's continuous everywhere from -1 up to infinity, and you can write it the way I wrote it just now, or the interval notation you see right there is that -1 comma infinity, and this time it includes the -1 because it's all right to get a -1 because that gives you a 0. Zeros are acceptable inside of a root, but that's where your graph begins at -1 and it goes straight to the right. Okay, so we get the sign chart, and this one's, it's either good or bad for students. I'll tell you that right now. You're either going to get this or you're going to hate it. It's one or the other, but I'll show you what it means here. So suppose you have a function continuous over the interval 1 to 8, every value between 1 and 8, not including 1 and 8, and the function does not equal 0 for any x in the function within 1 comma 8. So let me make sure, let me go back one slide here. Make sure everyone's seeing what I'm talking about here. They're saying between 1 and 8, this is going to be continuous. Okay? So I don't know what happens at 1, but let's just say that's an open dot, and let's say 8's an open dot. I don't know what it's going to do, but it's going to be one solid line, one continuous graph that I can draw, no gaps. Okay, that's all they're saying is it's continuous between them, but we don't know anything about it. Now we get another part that says there is no f of x equal to 0. Remember, this is f of x right here. It means there is no point right here on the x-axis. There's no place that crosses. So here's what we're going to try to figure out is, well, how does the graph look? Since it doesn't have any points here, that means it's never going to cross the x-axis between 1 and 8. There's no crossing. So it may be doing this, or it may be doing something like this. I don't know if it's bouncing up and down or it's a straight line, whatever the case, but it cannot go and cross up, because if you were to go here, at some point you're going to have to cross over, and it says there's no crossing. And it's continuous, so there's no jump, there's no hole, there's no gap in there. So how do we figure out? We can make a conclusion of what's going on here by the next line, which says, furthermore, further suppose that f of 2 equals 5. So that means we know we have a point at f of 2, and it's equal to 5. Let's get a 2. There's some point right here at 2 comma 5. Okay, so if I have a point above the x-axis, my question is it possible to have a point down here? Well, we kind of just talked about that. If we already know that 2 comma 5 is here, no matter what this graph does, if it's continuous, there's no way it can get down to here without crossing this line. So the conclusion is, if you know there's no crossing of the x-axis, once you determine one point, whether it's above or below, every single one of these has to be above or below. In this case, they all have to be above. I can't have any points down here. And that's what we're going to be doing here. Okay, so they asked that. Can f of x be negative for any x's? Well, the answer is no, and they kind of explain this a little more. That, like I was saying, if you were to have a point below the, that was a negative, below the x-axis, sorry, it would have to cross the x-axis. Essentially, it would be an x-intercept. You can't, they already said you had no x-intercepts, and if you're continuous, you can't jump down there. So it's like a wall, it's like a border, nothing can cross, so every point has to be in the same side, either above or below, in this case above, because of what they told us. And we're going to play this game with signs to try to figure it out. Now the next part's a little bit complicated. You can read that and see if that makes sense, but I'll show you excuse me, an example of what this theorem is saying. We kind of just talked about here. So here's how it's going to work. We're going to try to find an inequality, solve the inequality of this right here. Okay, x plus 1 over x minus 2 is greater than 0. We want to know, where does this function go above the x-axis? Where is it greater than 0? Where it's positive? So we let the fraction, the rational fraction, be the function. F of x equals x plus 1 over x minus 2. Now, we already know this. When x is 2, the denominator is 0, so that doesn't exist. Also, for fun, we're going to see, where does the top equal 0? And you see it's 0 when x equals negative 1. Okay, so our conclusion is x equals 2 is not in the domain, so it's not continuous there. But also, we have an x-intercept. An x-intercept at negative 1. That's our one place that makes the fraction 0. So do a number line thing. We do this here, and this partition number approach, and I do this pretty much the same way. We know there's a point here, and what I'm looking for is, I'm looking for special numbers. You're going to hear them called critical numbers later on. They're just important numbers. What makes the top be 0? Well, it's the negative 1. What makes the bottom 0? It's 2. So we know at 2, remember, it doesn't exist. It's probably got some sort of an asymptote. We don't know, but there's something going on there. There could be a jump. There could be something. There's definitely a discontinuity. At 1, negative 1, I'm sorry, that's where our graph is going to cross. Now, I'm going to show you a couple things. Your function could cross like that, or it could cross like that, or it could even hit it and bounce up, or hit it and bounce down. But all we know is something's touching at negative 1. Now here's the important part. They didn't really say this, but if you were to set that entire fraction to 0, and let's solve this. What we're doing is we're looking for the x-intercepts. So you let y equal 0, let the whole thing equal 0. Well, for a fraction equals 0, I can multiply both sides by x minus 2. All I need is the top to be 0, and that's how they got this negative 1. And what I want to point out is, this is the only x-intercept. There is no other place we can cross the x-axis, because if there was, we would have gotten more solutions here. We only got one solution, so this is it. So when we cross the x-axis, we cross it one time at negative 1, or we touch it at negative 1, and then we may have a hop over here at 2, but we'll talk about that. So what's going to happen is, we found our critical points. I like to do this where I kind of just, even though it's not an asymptote, I'm just making a border here. Even if you want to draw a solid line, you can. I want to see what happens to my function over here, what happens to it in this region, what happens to it in this region. Now, we talked about this already. Whatever we find out here, every point is either above or below. There cannot be any crossing, because if there was crossing, we would have found another intercept earlier. And there can't be any jumping there, because we know it's continuous in this entire region. How do we know? Because there is only one point. Oh, sorry, not that one. This point, x equals 2, that's the only place that there's a discontinuity. It's the only place our graph doesn't exist. So everything is continuous here, continuous here, continuous here. It's just this one point that's discontinuous. Okay? So like we talked about a few minutes ago, if every point in the middle is going to be continuous, then the entire graph is either going to be above or below the x-axis. It cannot cross it, because again, we don't have any other x-intercepts except for the negative 1. So here's how we do this. I'm going to take a point in this region, in that section, and it doesn't matter what point you pick. It could be 0, it could be 1. Don't pick negative 1, don't pick 2. You never pick the end caps, because we already know something weird is going on there. but you could pick a half, you can pick an eighth, you can pick a tenth, any number. I pick an easy one, and all I'm looking at in that function is, what is the sign of my answer? Well, I get a negative 1/2. So what that tells me is at 0, I don't even care where the point is. I just know at 0, it's a negative number. It's down here somewhere. Well, that means every point is going to be down here. Every single x value between -1 and 2 is going to be a negative number. They all have to be the same. So we test one point. This is what I call the test right here. You pick one point in the region. It's either going to be plus or minus, and that's what you get. Now I'm going to do the same thing over here. I pick any point to the left of -1. Can't pick -1, but I can pick -2, -3, -4. Now, again, you can pick a fraction like -1.5, but when you have a choice, why would you pick it? Pick something nice and easy. Well, the easiest one I can pick is, let's plug in -2. So when I find f of -2, I get -1 over -4, and all we care about is what's the sign. That gives me a positive number, which tells me every single number to the left here has to be positive. So I'm going to put a big plus right there. Every number is going to be up here in that region. And it can never cross down again, because remember, if it crosses down, we would have had another x-intercept, but we don't have any more. So every number, it may be bouncing around, it may be a constant, it may be straight, it may go straight up to infinity, but all these points on the left have to be positive. And then our last thing is we're going to test something in the right side. Anything bigger than 2. So my suggestion is pick the first whole number you see and plug that in. So let me just plug in 3, testing this right side. I get a 3 plus 1 over 3 minus 2. That gives me a 4 over 1. And like I said, all you care about is what's the sign. So everything on the right side of this, the right section I should say, is going to be positive. So you see what happens is our graph is going to be, we don't know yet, we're going to get to this in the next couple days, but it's doing something over here positive, then it hits that point, and now it's negative, and it doesn't hit this point because this doesn't exist. It probably just keeps going down to infinity, and then over here, maybe it resumes here, or maybe it does something like this, we don't know, but it's positive. We have partitioned our regions so we know where our graph is going to be positive, where it's going to be negative. And then back to the original question, where is it greater than 0? Well, it's going to be all these points from -infinity up to -1. We do not include -1 because -1 is actually 0. This is not an equals down here. It's strictly greater than 0. So we don't count the -1. We don't count any of the stuff in the middle because that's negative. And then we count the stuff on the right, which is everything from 2 on. And I put them together with the union, and that's the place where everything works. That's what we're doing here when we do these partitions, is you're just cutting up your number line, your graph, into 2, 3, 4 sections, and then you test every region. And remember, you check what points make it 0 on the top, what points make 0 on the bottom, and you're going to see what all of them are. Okay? Now this next part, I've already kind of done this, but they kind of talk about the partitions. And I like to visualize it with this number line that we just saw. And then all this slide is talking about is they're testing every number. They're picking something in each one. And now we know what's positive, what's negative, positive. And then we kind of see, this is a summary of what I just had. We knew everything in the middle is going to be negative. Everything on the right is going to be positive. Everything on the left is going to be negative. So our final answer, somewhere, well, it's not there yet. They asked for everywhere the graph is going to be positive. They didn't actually answer the question yet, but it was what I wrote earlier. Everything from -infinity to -1, no, not including -1, and then union that with everything from +2, not included, all the way up to infinity. Okay, so a partition number, just go back, that's these border numbers, the -1 and the 2, those critical special numbers I talked about. They're anywhere that the graph gives you a 0, an x-intercept, a 0 for the y, or it's any place that it's discontinuous. So those are the gaps. So they give you a nice little walkthrough on this one. Find all the partition numbers, so find out where the graph is equal to 0 and where the graph doesn't exist. And then you're going to check every one of the regions in between and around and see if they're plus and minus, and then you construct that graph, and then you can find out exactly where it's positive or negative. So here we get the same thing. A bakery estimates its annual profits from the production and sale of loaves of bread to be this function right here. Okay, now you may know how this graph looks, you may not. I'll give you a little quick one here. You look at your your biggest term. It's an x square. X square functions look like this, or they look like this. And the answer is, if that term that has an x square is positive, it's this one. If it's negative, it's that one. So we're going to have kind of a downward bell curve. All right? So now they're trying to figure out, where does it make a profit? So basically your function, if you don't make enough, it's going to be this graph down here. If you don't make enough, you're going to be below. If you make too much, you're going to be below because you probably won't be able to sell enough. So you're looking for that sweet spot in the middle of where we're making a profit. Now you don't have to graph this, but you have to find out this sign chart. You have to find out where the graph doesn't exist and where it equals 0. Now the first part, remember, it's a polynomial. X is a positive 1 power. This is a positive 2. That's a constant. Doesn't matter if these are negatives or positive. The signs, it's the powers we care about. It's a regular polynomial, so it's continuous everywhere. We know that from earlier. So we don't have to worry about where the graph doesn't exist. The domain is all real numbers. We do have to worry about, where does the polynomial equal 0? So there are it's continuous everywhere. Now we have to figure out where it equals 0. So we set the whole function equal to 0. Now what they've done here is they factored, and the part, I don't like how they did this, but what I would have done was, let's rewrite this where the highest power term is first, then the x, and then the 5,000 here at the end. Then they factored out this negative 0.01. Let me do it, yeah. So I'll put it right here. They pull out the negative 0.001. And remember, when you factor it out from every term, what you're doing is you're dividing that away. So that leaves me with an x squared, and then that leaves me with a, I want to say, minus 6,000 x in the middle, and then I think it's going to be a 5 million, positive 5 million over here. And then they factor this into negative 1,000, negative 5,000. So this is the factored approach right here. All right, and why do you factor? It's because remember, you have the function equal to 0. So the rule always, when you're solving, you set the whole thing equal to 0, you factor each piece, and then you set each piece equal to 0. Well, the first part you set equal to 0, it doesn't have an x, so there's no solution here. This one you set to equal to 0, you get 1,000. This one you set equal to 0, you get 5,000. So those are my zeros, 1,000 and 5,000. Okay, so this little extra, like I said, it was just to show you where they got those from when you're doing these examples later on. Okay, so now those are the partition numbers. Remember, where the graph is discontinuous, well, there weren't any of those, but where the graph equals 0, there are 2 of them. Those are my partition numbers. So we're going to make a number line, and we're going to have the 5,000 and the 1,000, and what happens is, and they didn't show this either, but we're going to find a number in the middle. We're going to test something in here. We're going to test something over here. We're going to test something over here. Now back to my function. This is where you test it. You always test numbers in the original, not even the factored one right here. I don't like testing in the factored one because if you messed up in your factoring, you're going to get the wrong answer. So always test it in the original function. So when we test, their suggestions were 0, 2,000, and 10,000. So when you plug in 0 to that original function, you get a negative number. That means everything on the left partition is going to be negative. When you plug in 2,000, you get a positive number. So every number in the middle partition has to be positive. And then last, you get a negative number, so they're all negative. Remember that graph I told you earlier? Does something like that? These are the places where it hits the x-axis. This is the place so you know the middle is where it's positive. So our conclusion is, as long as you sell between 1,000 and 5,000 units, or produce, I guess would be the answer, then you know you're going to make a profit. But if you sell not enough, you're in a negative. You sell too many, you're going to be in a positive, and that's the kind of application we can use here, for your business stuff. The whole reason you're in this class. All right, so let's look at some problems here. So again, back to our course home, you'll see what you've completed. Obviously, I'm not doing all of them, so you see my score is pretty bad here. And remember, just a quick reminder, your score that matters is what you get on the quizzes. The homework is just the forced practice that I have you do. The quizzes are all that matters. But as you learned, if you don't get high enough on the quiz, you can't take you don't get a high enough score on the homework, you can't even take the quiz. So you have to make sure you're completing those homeworks to open up the quizzes to take here. So let's look at our assignments here. We're now on homework number 4 for this week. Kind of do what I always do. Let's start at number 3 and just kind of go by 4s here. And let's see what everything has got here. Okay, so on this one, write the given set in an interval notation and graph it on a number line. All right, so interval notation. Now, if you haven't seen this notation, this just means the set of all x's such that x is in between 2 and 8. Okay, really you don't need all this. It just means this right here, everything between 2 and 8. So when I do interval notation, I'm including, remember too, so it's interval notation. It's always going to be small to big. All right? Sometimes it's a bracket, sometimes it's a parenthesis. It's do you include it, not whether it's positive, negative, or 0, or infinity. Infinities always do have the parenthesis, but other than that, we have to start with our smallest. So I know it's going to be 2 to 8 because there's an equal sign right here. That means the 2 is actually acceptable, so we equal that. And then also, this parenthesis or bracket has nothing to do with if this is going to be a parenthesis or bracket. We look at this equal sign touching the 8. That also means that, so there is our interval notation. Now we have to look at the number line and figure out what are they saying. Well, this one, let's start at C. This has all the points from 2 going up forever. Well, we know it stops at 8 because too big isn't going to work. So it's not C. Definitely that one's out. A, B, and D all look alike because they all go from 2 to 8, but you see some include, some don't. So go back to your interval notation, go back to this. We are including both 2 and 8, so it's not A, it's not D, it's going to be B. Okay? So that's just kind of, these first couple just kind of getting you warmed up on the graphs to make sure you know how they look. Number 7, use the graph in the function shown to estimate the indicated function. Now make sure you know what they're asking for. If they want a limit, they're going to say what's the limit as x approaches some number. Notice there's no limit here. They're not asking for a limit on part A, or the only part here. They just want to know what's f of negative 1.9. So let's look at our picture here. Let's see what we get. So if you have to, you can always zoom in a little bit more. What's f of negative 1.9? Well, you make sure you know the scale of our picture here. Here's negative 1. And remember, that's your x-axis right there. Negative 2, negative 3, negative 4. So they want negative 1.9. That's right around here. Okay? So it's that point they're asking what's the y value right there. They're not asking the limit. They're asking what's the y value. Well, this looks like it's going up pretty steady. There's a 1, there's a 0. I'm going to guess it's around 1.9 because it's a nice, perfect 45-degree angle. See, we have a negative 1. We have a negative 2. It looks like it's rising up at a constant slope there of negative or positive, negative 1, I'm sorry. So it looks like this is a point, negative 2, positive 1. So if we're just 1/10 over to the right, looks like it's going to be 1/10 down. So I think it's going to be just a 0.9. And we check it. This is what you learn on the homework, and that's what we have. Okay? So let's look at some more of these. Let's go to number 11. And again, make sure you read the question that's being asked. Don't just, jump in there. So it's kind of the same thing, though. They are asking what's f of negative 2.9. don't be afraid to, you may not be able to write on your screen, but kind of make sure you know where you're at here. -1, -2, -3. So -2.9 is right here, and they're asking what's the y value. Okay, now, again, I'm looking at these points. F of -2, it doesn't exist, but the limit is right around 2. Okay, so I won't write that equals. The limit is at 2. So this point right here, even though it doesn't exist, this is -2, +2. This point right here doesn't exist. That is about -3, 1. So what I want you guys to see is that this is going at a nice 45-degree angle, which is a slope of 1, which means we should have the same sort of change. As we add 1, we go 1 up. When we add 0.3, we add 0.3 to the y value. So at -2.9, it looks like it's going to be right around 1.1. Got all my mess right here, but if I type in the 1.1, it should be good, and that's what we have. So that's all these are, is just kind of doing your best guesstimation, but in some cases, that's the actual answer. It's not even an approximation. That's the actual answer because it's a nice, perfect slope. Now, as you start seeing these next ones, you're going to see that it's not going to be a nice, perfect picture. So we're going to have to do a little bit more work. So let's look at number 15 here. So in this one, determine where the function is continuous. Okay, so think about this. It's a rational function, but what we need to find out is where the function doesn't exist. So I'm going to start by taking that denominator. I want to know where that thing is 0. What x's make that 0? So this is my normal plan. Let's solve this. Well, let's square root both sides, and you'll see right here, I can't square root a negative. That can't happen, which means this thing is never going to have a bad number on the bottom. It's going to be good everywhere. So the top is always good, the bottom is always good. For a rational function, the only bad places, remember we had either a theorem or a property earlier today that said for a rational function, whatever x's make the bottom 0, that's where it doesn't exist, and it's also where it's not continuous. Well, it looks like everything is going to be continuous because it all exists. So to find my parenthesis. It's my negative infinity here. There it is. Negative infinity to positive infinity, and there's our answer. Okay. Now, it was kind of deceiving back there. If you notice, that initial palette that I used to click down here in the bottom, it didn't have all of my it didn't have my infinities on there. So don't feel that, hey, I thought it was going to be infinity, negative infinity to infinity. Just because you don't see it in that palette does not mean you were wrong. You had to click the more like I did to show more buttons or more options and plug that in there. And sometimes, and I'll try this out here, sometimes you can type the word INF. Yeah, it didn't work. Some calculators will allow you to type that for infinity, but this one you've got to go find this right there. So we'll get to that if that's an infinity on this one. So same question. Oh, let me go click a few more here. So that was number 15. Let's look at number 19. Use a sign chart. And this is what I wanted to do here to make sure we're all understanding that sign chart. So remember the sign chart. We set the top equal to 0. Okay, that's our first thing. That's going to tell us our x-intercepts. So in order to do this, I have to factor that top, and I set each piece equal to 0, and it looks like I get x equals 0, x equals -5. Okay? Then I need to see where the graph doesn't exist. And remember, that's the discontinuity. I don't know if I spelled that right, but that's the discontinuities. So we set the bottom equal to 0, and you see it's at 2. So we have all these places, so I'm going to take my number line, and make sure you do them in order. There's a 0, and it doesn't have to be perfectly scaled. Oh, sorry, I missed the important one. Start with the smallest one. I started to say that, but I missed it. -5, then the 0, then the 2. And like I said, don't worry if these are not scale. This is just for us to get an understanding of what's happening in our partitions. So remember, there is a point on the x-axis at -5. There's also one at 0. There is a discontinuity, so I'm going to put a little red X right there at -2. This doesn't exist. Okay? But these are the only places where you have a chance to jump over the x-axis or cross the x-axis. So remember, the next step is we need to test in every region. Test all 4 regions in this case. And all we're looking for is our function positive or negative? Okay? So I'm going to clean up some of this on the right. And so what I'm looking for is, in my original function, do I get a positive or do I get a negative when I test a number from each of the 4 regions? You just got to test one from each. So the function, remember they rewrote the left side, the fraction, as a function. Okay, now in the beginning, I'm going to have you just plug it in, and then I'll show you some shortcuts later on. But let me start right over here. Let's plug in 1. So when I plug in f of 1, I get, and like I said, here's the good part here, I get 1 plus 5. I only care if that top is positive, and I care if the bottom is negative. We get a positive over a negative, which means we get a negative right here. Plus divided by minus. You can really break this down into 2 pieces, top and bottom. And if they're both positive, it's a positive. If they're both negative, you're going to get a negative, because when you divide negatives, they cancel. If one is negative, one's positive, then we have something else we do. So let's test a -1. Now I'm going to save the writing a little bit, so I'm going to kind of do this over here each step. If I can erase this. Just to save a little bit of time, I'm just going to show what I'm doing here. Okay, so let me give myself a little more room. All right, so we're going to test -1. So that gives me a -1 squared is a 1 minus 5 all over -1 minus 2. Make sure you do your math right. This looks like a -4 over a -3. That gives me a positive in this region. And remember, you only have to get one representative, one test number per region, per partition. And once that is positive or negative, assume you did it right, then every number in there has to be that one. Okay, let's go to the far left. Let's test, probably the easiest number to test is -6. It's the smallest number that I can pick that's past -5. So that gives me a 36 minus a 30 all over a -6 minus 2. That gives me 6 over -8. And like I said, all we care about is what's the sign. Yeah, it's -3/4. I don't care about the 3/4. I just care that's negative. Now you may be looking at this and saying, oh, it looks like it's going back and forth, positive, negative, positive, negative. That is typically what happens, but it's not a guarantee. So I'm going to tell you, you need to test all the regions. Don't just assume there's a plus here on the end. It's probably going to be a positive, but I'm not going to assume that. I have to check every region, because there will be graphs, believe me on this, where it will go like minus, minus, plus, plus, or something not according to pattern. Typically the pattern is alternating, but not always. Okay, and you'll get into some more of those nuances later. So over here, this final region, let's just test 3. We get 9 plus 15 over 3 minus 2. We get a positive over a positive, so that is going to be a positive. All right, so we know where our graph is going to be above and below the x-axis. Now, go back to this question. They ask, where is it greater than 0, which means they want to know the positive regions. And remember, you never make it equal to this discontinuity. So that's never included. But now the question is, what's up with the -5 and the 0? Because this graph does not have an equal sign, you also will not include those. So my final answer is going to be everything between -5 and 0, not including those. Then union that with
everything from not including 2 all the way up to infinity, not including the infinity, and there's our interval notation. Oh, what did I miss here? -5, 0, greater than 0. Okay, they may not have liked my symbol. I put a capital U in there. Okay, I gotta read what they don't like about this here. Factor it. All right, I hope this is not an error. Okay, I see my problem. I read it wrong. They didn't ask for interval notation, they asked for inequality notation. So inequality notation is going to be where they say x is in between -5 less than x less than 0, like that. Or, I don't know, there's an or symbol. Sometimes they use an or symbol, sometimes they don't. Or x is greater than 2. That'll tell us our rate. It's the same answer, but there we finally get it. But it's an inequality notation. I'm sorry, I missed that. I just ran right through that one here. Sometimes they, I saw it the same. Now they want the interval notation, and I've not really seen this called inequality notation too much, but this is why we're all doing the homework. Got to make sure we are answering the questions the same way. Now back to that interval notation that I had earlier. Hopefully that was right. -5 to 0, not including either. Union that with 2 up to infinity. And if this first one's right, this one is, I'm just building off of that. It should be good. And there we go. Okay, so like I said, sometimes you're going to run into that where we had the right answer, but we answered it wrong, and you keep answering it wrong. It's like a password that locks out on you. Now you have to do the whole problem over. And unfortunately, that does happen sometimes. But here's how I look at it. You'd rather do it there than on a quiz where it actually counts. You'd rather learn the nuances of this. So look at that as not a bad thing. Okay, number 23. Here, f of x equals the square root of x squared minus 100. Now remember, start with the inside. That right there is continuous everywhere, because it's a regular polynomial. It doesn't matter if it's a negative. It's continuous. Remember drawing the graph without lifting up your pencil. But now that it's in a square root, if that was a cube root or fifth root, no problem. This will still be our answer. But because it's a square root, now we have to say only places where it's positive or 0. So we set the whole inside greater than or equal to 0. And now we have to figure this out. Don't move the 100 over. When you have an inequality, you have to factor. So if it was a regular power of 1, you just set it, you move it over and you divide or do whatever. But when you have a polynomial where it's 2 or more is your power, you leave it all on the one side and you factor. And now we're going to make our partition again. Because remember, I want to know, where does this actually equal 0? And where does this actually equal 0? Well, we get an x equals -10. We get an x equals +10. So that's what we're trying to figure out. Okay, we are allowed to equal it, but what we have to do is we need to make that partition again. We need to figure out what happens to the left and what happens to the right and what happens in the middle of our critical numbers. These are the actual zeros that we have. Okay, so now we test each region. Let's test a 0. And remember, when you're testing it, we're going right here, by the way. This is where I'm going to test in. Now, you can test into that function right there, but if you do, what you're going to get is not a negative, you're going to get a non-existing, because you're going to get negative inside the root. We're just caring about when is the inside greater than or less than 0. So if I plug in 0 right here, I get 0 squared minus 100. That's a negative, so everything in here is negative. If I plug in 11, oh sorry, that's supposed to be +10. Fix that. If I plug +11 into this function, I get 121 minus 100. That's positive. If I plug in -11, I get a positive. So what we're looking for, remember, is everywhere our graph is greater than or equal to 0. So it's all these points up to -10 and including -10. Because remember, it's got an equal sign down here. And also, all the points from 10 going on to positive infinity, like that. Now let's make sure I answer the question correctly based on what they said here. They want this it's continuous on the interval notation. So this time they want interval notation. So we get negative infinity up to negative 10. And remember, we include the negative 10. And this time I'm going to try that capital U and see if it actually works. This is me testing it out on my first run at this. From 10 up to infinity. Another thing, notice I wrote positive infinity over here. I love to do that as well. That I know won't make a difference, but you can just do positive or regular. And let me erase some of this so you can all see what I've just drawn in here. Okay, there's the answer, and notice I had a 0 instead of a shift, 0. Check the answer. Okay, it didn't like it. Now my guess was it didn't like my capital U, so let me try an actual union. And now it's correct. So that's the lesson. You all learned that from me here. Don't use a capital U. You got to use that union symbol in the answer there. Okay, so that was it for that one. Let's look at, I think the next one is 27. Yeah, let's try this one. Okay, statement. If the statement is always true, explain why. If not, give a counterexample. Well, they say a polynomial function is continuous for all real numbers. Well, a couple of things here. First off, it's true because we talked about that. Polynomials exist everywhere, and because there's nothing on the bottom to make, go out of the domain, there's no gaps, there's no jumps. It's just one nice continuous thing. So it's definitely not A and B, no falses. Then we look at here, a statement is true because for any positive integer of n, x to the n power is continuous for all real numbers. Remember, we had that earlier, and that is true. All of these, they're not going to work. Because let's look at D. It's not false on this one because the counterexample is this. That's not a polynomial function. That's a rational function. Okay? This is a polynomial function in A, but it's continuous everywhere. So that's not a good counterexample. This one, the rule is if the inside is continuous, well, that is continuous everywhere greater than or equal to 0, but when it's a square root, it's not a polynomial either. So this is my answer right here, and we're done with that. So you get a couple of these just to kind of see if you're understanding the concepts. To me, I'm going to tell you the most important part is, do you get how to go, how to use these problems, how to work them out? All right, we'll do this last one here. First class postage is 41 cents for the first ounce or any fraction thereof, meaning anything a fraction of 1 ounce, it's still going to be 41 cents. Then 15 cents for each additional ounce or fraction thereof, adding. Maximum weight is 3.5 ounces, so up to a maximum weight of 3.5 ounces. After that, it's going to be something different, okay? So they want us to write a piecewise graph for a first-class postage stamp. Now remember, these are those graphs where, depending on what x is, we have different values. Well, let's start with the first one. Remember, if it's greater than 0, up to 1, it's 41 cents. So I'm going to put the 0.41 in there. Now, if it's 1 ounce, it's 0.41. If it's 0.5, it's going to be 0.41. If it's 0.9, it's going to be 0.41. Notice there's no variable in here. It's a constant 41 cents, no matter how much it is. Then the next group between 1 and 2, anything higher than 1 all the way up to 2, that's 1 ounce more, it's going to be 15 cents more. So it's essentially 0.41 plus 0.15. It's not just 0.515 because we all know it's not going to be less than this one. It's got to be higher. So you can say this, or what's even better is just add them up and get that 56 cents. Okay? That's what we have right there. And then 1 more ounce, we're going to add another 15 cents. It's going to be 0.71. And the last one's the weird part, okay? So notice we're at 0.71, right at 3 ounces. If you go just a little bit over 3, it's going to be another 15 cents. So I'm going to go to the 0.86, but it stops at 3.5. That's our end. Anything after that, now we have something special. So it's a weird question, but this is what they're asking for. What's our piecewise graph? You'll see the picture in a second, but that's how you write it out. It doesn't matter what the x is, because the x is, go back here, whatever the x is, whatever region's in it, it tells you. It's like a table. It doesn't go up like a slope. You'll see the graph in a second how it looks. Everything greater than 0, between 0 and 1, not including 0 and including 1. So I'm going to focus just on this. When x, there's going to be an open dot at 0, there's going to be a closed dot at 1. Everything in between there is right at 0.41. It doesn't go up or down. It stays at 0.41. So I got to find my 0.41, and it looks like I have it right here. Okay, and remember, open dot at 0, closed dot at 1. This one, it's too high. This one is too high. This one's the right level on D, but it's got a closed dot, open dot. It's in the wrong spot. Every one of these, this is the only graph that works right here. And I'm going to show it a little bit larger so you can kind of see it. Let's go here. Okay, so at 41 cents, notice this is the weight down here. This kind of is actually, I think, better than looking at the graph here. Let me see if I can do both. Okay, so here's our function. Like I said, I think the graph explains it more. If it's a little more than 0, because you can't weigh anything that weighs 0. You can't send anything that weighs 0. So it's anything just above 0 up to 1 ounce, including 1 ounce, it's 41 cents. So whether it's 0.5 ounces, 0.9 ounces, 0.75, 0.999 ounces, every one of these has the same price. If you've mailed something, you know this. Everything from here up to here, it's all going to be 0.41. Once you get over an ounce, now you pay 15 cents more, so there's where the 0.56 comes in. Everything between 1 and 2, whether it's 1.1, 1.2, 1.5, 1.9, or even 2, they all pay the same price. That's 0.56. So that's why it's not a diagonal line. It's a step function is what these are called. So once you hit a certain barrier, you step up to the next one. And even though it might seem unfair that a 2.1 pays the same as 3.0, that's how the formula is set up. That's how the definition of the postage is going to work. And then, of course, your last step up to here, that's why this is our answer on B. So let's check that, and that's it. And part C says, is the graph continuous? Well, let's pull it up again. You can definitely see it's not continuous, but why? Remember our rules? Let's look at our reasons. So definitely it's not yes, because we know there's gaps in our function here. Okay, huge gaps. Why? Let's see. Let's look at the explanation. It's got to be one of these. You have to give a reason. No, because P of 2.5 doesn't exist. Well, let's see. Where's 2.5 right here? Does the actual point exist? Yeah, it does. There's a point right there. So that's not a good enough reason. Well, let's look at the second one. The limit as x approaches 2.5 does not equal 2.5. Well, let's look at the picture again. At 2.5, as we come in from the left and we come in from the right, we're approaching the same value, which is that, what is it, a 0.56? They're approaching the same number, so the limit exists. It's 0.56. That is also the y value at 2.5. They are equal. This says they're not equal. Well, let's look at the last one. All right, no, because the point doesn't exist at 2.5. Okay. Okay, let's go back. I'm sorry. I wish I can rewind this. Let's just ignore everything I just said. They're not asking if the graph is continuous. Okay, I hope you're learning all from me what not to do here. Sorry about this. They're not asking if the graph is continuous. They're saying, is it continuous at 2.5? At the actual point. Okay, let's look at this again. I'm sorry. 2.5, is the graph continuous right here? The graph is not continuous in the whole thing, but in this immediate section around 2.5, the question is the graph continuous? So they're asking right around there. So it's almost like if you can only look at this little immediate area and zoom in there, is that continuous? That one is. Okay, so that exists. What I've kind of found here is I've kind of proven this already. Let's just look at everything, show you what I mean. Okay, so we already said this is not true because the graph does exist here. We said this is false because the limit does equal the point. Over here, it's not true because the limit actually does exist. So the only choice is this one. That's how I knew I read the question wrong. Because the limit exists, it does at 2.5. and the limit which exists equals the actual point. That is actually true. So apologies again. I was giving you the answer to this. They're asking, was it continuous right there at that point? And the answer is yes, it's continuous. And this is the reason, because the limit exists, the actual coordinate exists, and they're equal. Those are the three criteria that we had earlier. So that's why the answer is the third choice for part C. And is there another one? Yeah. Now, is the graph continuous at x equals 3? Let's look at it. At 3, I can definitely see there's a jump here. Okay? So I know it's not going to be continuous at 3. Why? Okay, so it's not this one, because the limit does not equal the point. Well, the limit doesn't actually exist right here. Go back to the graph. See, at 3, there is no limit, because coming from the left, it's approaching 0.71. Coming from the right, it's approaching 0.86. So there is no limit. So that's what I'm actually going to key on here. And this is my choice right here, because the limit does not exist. The point actually exists, by the way. At 3, the point is right down here. It's that 0.71. So the coordinate exists. So not this one, not this one. And this one, technically I can say that's an answer, but this is the better answer. That's why you got to read them all. It's because the limit does not exist at all. Okay? And that's it for 31. Now at this point, I think the rest of them are going to be from section 2.4, so I'll stop this video here. I'll record another one for 2.4 coming up, so you should be able to get through at least number 30, 31, 32, somewhere around there. And then, like I said, you've got all week to do this. Homework number 4. Obviously, make sure you get your quiz number 3, which is on last week's homework. All of those 3 sections, make sure you get that in by Monday night at the end of the night here. So make sure that's in by midnight, submitted by midnight, not started by midnight. So if you have any questions on section 2.3, anything I talked about, shoot me an email and I will tell you everything I can. Okay, have a good one.